Okay, hopefully everybody can hear my voice, otherwise they're looking at me pointing at this sign and hopefully getting their sound up and running. This is the lesson on Chapter 11, Section 6. It's actually the first thing we talked about in Chapter 12. It goes better with Chapter 12 than Chapter 11, so we've decided to group it with Chapter 12. Anyway, this is the Chapter 12 study guide in geometry. And it is all about volume and surface area of figures and three-dimensional objects. So, section 11.6, we start with some basic definitions. The center of a polygon is basically the center of an circumscribed circle. So basically, if you have a polygon that looks like that, and you draw a circle around it that touches all the vertices, and obviously I'm drawing too quickly to be accurate here, but there we go. That's a circumscribed circle. It goes around the outside and touches all the vertices. So whatever the center of that circle is also the center of the polygon. The radius of a polygon is the distance, is also basically the radius of this circumscribed circle. So if you go from the center of the circle to any point on the circle, that would be the radius of the polygon. Now, an apothem is something different. If I have, let's say, a pentagon, let's see if I can draw one here, like so. The apothem would be the distance from the center. Again, if I drew a circle around the outside of this, whatever the center of the circle would be is the center of the polygon. The apothem, and we're going to use this a lot, so you need to know this, is the distance between the center and the middle of one of the sides. So basically from here to here. It's a length that we have that's part of a lot of formulas that we use, so you're definitely going to need to know what that is and where to find it. The central angle of a regular polygon, well, I'm going to actually draw you some examples of what central angles are, but basically if you have a radius and then you draw a radius that's next to it, remember a radius connects the a vertice to the center. If you have any two radii, the angle between them is called the central angle. Now, I'm actually going to, should I draw some pictures in the back on this one? Maybe. I might come back to that concept and talk a little bit more about central angles. But basically that's what it is. It's an angle that's in the center of everything, the vertex that is, and it's measured like so. So you can see in example 1, they've got some preliminary questions for us. This is a hexagon. Remember, hexagon has 6 sides. 6 has the letter X in it, and so does hexagon has the letter X in it, so that's why I remember that a hexagon has 6 sides. In the diagram, A, B, C, D, E, F is a regular hexagon. That means that all the side lengths are the same. Okay? And find the measure of each. Well, if we want to find the measure of angle EGF, that's this. That is a central angle. So I think I am actually going to talk a little bit more about central angles right now. So what I'm going to do is I'm going to use the pages in the back of the note-taking guide. There is one extra page back here that's blank front and back, and I'm going to use that to basically talk about central angles. Now, I'm not just talking about all central angles. I'm really focusing specifically on the central angles inside regular polygons. As you know by this time in geometry, a regular polygon is a polygon where all the sides match in length. So with this type of example, I'm just going to draw some regular polygons and then talk about the central angles inside. So the first one is a regular triangle. That means, again, regular means all the sides are the same length. So I'm going to do my best to draw a triangle where all sides are the same length. Fairly good. Okay, now if I carve this triangle from the center, if I draw a radius here, and a radius here, and a radius here, I've carved it into 3 equal pieces. And each one of these is a central angle. So a regular triangle will have 3 central angles. Now, as you can see, basically if I add up all 3 of these angles, it'll give me a total of 360 because it gives me a full circle all the way around, right? And if each of them is equal to each other, then if I take 360, which is the full circle, and I cut it into 3 equal pieces, to find the measure of just one, I can take 360 and divide it by 3. So each one of these central angles is 120 degrees. Now, as you may imagine, you don't get the same type of thing for a square. A square is a regular quadrilateral. So again, I'll find the center and I'll draw all the radii that I can. There will be 4 of them. And then when I draw all the radii in, then all of the central angles are visible. You have a central angle here, and here, and here, and here. So how much is each one of these central angles? Well, they're all the same as each other, and they add up to a full circle, which is 360 in degrees. So to calculate each one, we could take 360 and divide it into 4 equal pieces, and we get, as you may already have figured out, 90 degrees. We can do this for a pentagon. Again, I tried to draw it as best I could as a regular shape, meaning that I tried to draw it where all the sides are equal in length. I think that's about as good as I can do. I'll find the center of it as best I can estimate. And then I'll draw all the lines that are the radius lines. There you go. So we can now see the central angles. We have 5 of them in a pentagon, like so. So as you can see again, they all add up to 360 degrees if we go all the way around once. And to figure out the measure of each one, we'll take that 360 and we'll divide by 5, because each of them is the same as the others. So we get 72 degrees for each central angle on a regular pentagon. Remember, the shapes have to be regular. They have to have congruent sides, side lengths, in order for this to be true. We'll do one more example. See if I can draw a regular hexagon. Okay, not bad. I think the center will be about right there. I tried to draw this shape, 6 sides, all equal in length to the other sides, each one. there is my regular hexagon. And if I draw in all the radii inside, there should be 6 of them. And then these are all my central angles. I again have 6 of them. And again, you can see that if you add all of them up, they'd add up to a total full circle of 360. So to figure out the measure of just one, I want 1/6 of 360, or if I take 360 and divide it by 6, I get 60 degrees for each central angle in a regular hexagon. Now, obviously you can do this forever. You could draw a 7-sided shape called a heptagon and take 360 and divide by 7 to figure out what each central angle is, or an octagon, a regular octagon. If you wanted to figure out the measure of each central angle, you'd take 360 and divide by 8, and so on and so on and so on if you wanted to. So, now that we have a good idea of what a central angle is and how to find it when you're dealing with regular polygons, let's go back to our example on the first page. Okay, so we were talking about here a hexagon. And as you can tell, it's a regular hexagon, and so all the central angles would be the same. So if I drew in all the radii all the way out like so, you'd see we'd have 1, 2, 3, 4, 5, 6 equal sections, and each one of these angles is your central angle, and really they're asking you to find angle EGF, which is this central angle right here. So for part A, because it's a central angle, I'll just take 360 and divide by 6, and I'll get 60 degrees for this central angle right here. Now they want us to find angle EGH. That's half of that, because this triangle right here is isosceles because the radius here and the radius here are the same length. I know that that this line right here, being the apothem, cuts that triangle in exactly 2 equal pieces. So for part B, I know that this line right here cuts the triangle in 2 equal pieces, and therefore angle EGH, which is this half of it, can be found by simply taking the full 60 degrees from here to here and just taking the right side. Dividing by 2 gives you 30 degrees. And then finally C, they want you to find angle HEG. So that's this corner down here. So basically this half of the triangle up here, I'm going to draw that a little bit bigger. Okay, so it's just the right side right here. This corner is 90 degrees as it was marked. We figured out that the top corner up there is angle EGH. That was part B, that was 30 degrees. And so for part C, if I know all 3 angles inside a triangle add up to 180, I can take 180 minus 90 minus 30, and I end up with this corner right here, which happens to be 60 degrees. Okay, next page. Theorem 11.11. All right, now this is a formula that you're going to use a lot in this chapter, and as you can see, they've drawn the apothem. These are the radii, 1, 2, 3, 4, 5, 6. Now this formula works for all polygons. They happen to have drawn a hexagon here, but it works for all polygons. So just be aware of that. These are the 6 radii, and then this right here is an apothem. Remember, an apothem is different from a radii. A radii goes from the center out to a vertex on the polygon, but the apothem goes from the center of the polygon to the middle of a side. And this little apothem is going to be part of our formula. It's most likely a formula you've never seen before, and here it is. The formula says that for any regular polygon, You can find the area by multiplying 1/2 times the length of the apothem times the perimeter of the shape. So you could find the length of one side and then just add that to, multiply that by how many sides there are to get the perimeter all the way around, for example. Or sometimes they just give it to you. The perimeter is this much. Now, obviously, you can write the perimeter as n number of sides times s, which is the length of each side. Number of sides and s is the length of each side. Obviously, if this side length is 5 and there's 6 sides, I'd go 5 times 6 to get a perimeter of 30 all the way around. Most of you already know how to find perimeter. It's kind of obvious, but they broke it down into number of sides times length of each side as an alternate way of thinking about the perimeter. So these formulas are the same. It's just that this one breaks down the perimeter and this one just states it as P. Okay, here's a real life example. This is a wooden coaster, meaning it's something that you put your drink on to prevent damage to a tabletop. A wooden coaster is a regular octagon, which means it has 8 sides and all side lengths are the same as the other sides, and a radius of 3.92 centimeters. What is the area of the coaster? So I'm going to go ahead and use this formula up here. I'm going to try to find the perimeter of this shape, and then I'm going to try to find the length of an apothem. Now, they did not give me an apothem length. They gave me a radius shape or length. Now, the perimeter is pretty easy to find because they actually gave me one of the sides is 3. So that means this is 3, and 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 that's 3 as well. So basically, a short way of finding the perimeter, as given in this formula up here, is the number of sides, 8, times each side length, which is 3. Remember, this only works for regular polygons, not for just any old polygon. Okay, so the perimeter is 24 centimeters. And now that's one of the 2 things that we need to find to use this area formula for regular polygons. The other thing is the apothem. Now, this is going to be a little trickier, but here's what I'm going to do. If I take this side right here, which is 3.92, and I draw from that same center, I draw an apothem down to the middle of this side over here, like so. Then I have a right triangle. This is a 90-degree angle as I've drawn it. So this side up here is the apothem. And then this length down here, since it's drawn exactly to the middle of the side and the whole side is 3 centimeters, right? Then half of that would be this much, right? That would be 1.5 centimeters. So I have a right triangle where I'm trying to find one of the leg lengths, which is my apothem. I have one leg length of 1.5 centimeters, and I have the hypotenuse length of 3.92 centimeters. So a formula that we work with a lot is the Pythagorean theorem, and that says that leg squared plus leg squared equals hypotenuse squared on any right triangle that we can find. So I can use this formula to find the length of the apothem that we need, and then we'll have all the numbers we need for our formula. So I'm going to square 1.5, and then I'm going to square 3.92, and then I'm going to subtract 2.25 on both sides, solving and isolating a squared. And then to find the apothem length, I'm going to have to get rid of the square by doing the opposite of that, which is a square root, and doing it on both sides. I get the apothem to be approximately 3.621657. Oops, not on the screen. There you go. Okay, so the area of the shape, we're using this formula up here, is 1/2 times the apothem times the perimeter. So that is 1/2 times the apothem, which we calculated down here, 3.621657, times the perimeter of 24. So if I multiply all that together, I get approximately 43.5. This is area, so it's going to be in square centimeters. Remember to put the square here, not here. And there you go. All right, so this is a square. They want to find the angle FKJ. Well, this is a central angle, right? Because it's one of our 4 equal measured angles inside of our square. That's 1, 2, 3, 4 central angles here, right? So if I take the full circle 360 and then divide by 4, I get 90 degrees. So that's the measure of angle FKJ. FKJ, right there. Now the measure of KJF would be basically if I take this right triangle right here. This angle up here is half of 90, which will be 45. And so this other corner would be, using the fact that any triangle, the interior angles add up to 180, would be 180 minus the other 2 angles, 90 and 45. So I would get 45 degrees for the measure of angle KJF. Now number 2 is very similar to the very first one we did over here. This real life example about the wooden coaster. They give us a lot of the same information. They give us the one of the side lengths here, and they give us a radius length, which is the same given information over there. Obviously this is not a hexagon, this is a pentagon. Or no, I'm sorry, that was an octagon. This is a pentagon. But like I said, the 2 basic given pieces of information are the same. A side length and a radius. And they also want us to find the area. So the area is 1/2 times the apothem length, which we don't know, times the perimeter of the shape. So we'll need to find these 2 values. I'm going to start with the easy one, that's the perimeter. The perimeter here, it's a regular pentagon. So that's how I know that all the sides have the same length. And so if this is 8, then this is 8, then this is 8, and this is 8, and that's 8. So there are 8 sides, all with a length of 8. I'm sorry, 5 sides, all with a length of 8. So a number of sides, 8 times, or 5 times the length of each side, 8. Anyway, it's 8 times 5, which is 40 inches, all the way around. Okay, now what I'm going to do is I'm going to drop an apothem down from here. If I drop one down to here, as straight on as I can, will give me a 90-degree angle. This is exactly half the length of the side, because I tried to hit the middle position. So if the length of the side is 8, then exactly half of it, that's this one, would be 4, right? So this is a right triangle. The hypotenuse is 6.8. One of the legs is 4. And then the apothem, that's what I'm trying to find to complete all the things I need to find for my overall area formula, is the other leg. So I'm going to use the Pythagorean theorem here that says that leg squared plus leg squared equals hypotenuse squared. So that would be a squared plus 4 squared equals 6.8 squared. So I get a squared plus 16 equals 30.24. Oops, I'm sorry, 46.24. And then I'm going to subtract 16 on both sides, which gives me a squared equals 30.24. And then I'd like to get rid of the square on my a. So I'll do the opposite of that, which is the square root. And doing it on both sides, I get that a is approximately 5.499. That's our apothem. So now we have enough information to put it all together in our formula. So I've got 1/2 times 5.499 times 40. So I have an overall area of 109.98, and they inches squared, but they want me to round this off to the nearest square inch, so that would be approximately 110 square inches. The next one is an example based on a regular nonagon. That means it has 9 sides. And regular, again, means that all the side lengths are the same as all the others. They are all congruent. Now here they don't give us very much. They give us a radius, and they give it to us twice, but that's basically it. So we may have to do a little bit more work on this one to figure out all the numbers that we need. So remember, to find the area of a shape that is a regular polygon, we multiply 1/2 times the apothem, which we don't have, this length here, times the perimeter, which we also don't have. So we're going to need to figure out each of these, the apothem and the perimeter. How do we calculate? Let's start with the apothem. If I take this and draw that from the line from the center of the circle to the middle of the side, that's your apothem, right? So basically I'll draw it down here. And I'm going to draw just the top part of this triangle. Here's K, L, and M. Okay. Now, since this is a nonagon, there's one more thing that I can figure out, and that's how wide each central angle is. So if I draw all of the radii in here, now obviously this line right here is not a radius, that's an apothem, right? This little line right here. I'll draw it in as a dashed line, perhaps that'll be better. Okay. So all the lines that are solid now are radii, and in the center here, because there's 9 of them, you have 9 central angles, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and they're all equal to each other. So we can figure out the length of a central angle, which basically gives you the distance all the way across this triangle here. The large one, not the half. So we can figure out the central angle by taking 360 and dividing into 9 equal pieces. So that's 40. So each of these is 40, including this one. Well, that would be the distance across the whole triangle, but this is just half of it. So if the full distance is 40 here, this is my triangle, the full one, and we're just taking the top half of this triangle, right? That means that this corner up here would be half of the central angle, which would be 20 degrees. Half of 40 is 20, right? This is 20 and that's 20. Now, the reason why that's helpful is that that's the only other piece of information I'll be able to figure out at this point about the triangle. Now, I need two things. I need to figure out the apothem, and then it would also be helpful to figure out how long this side is here. Because if we know that this is half of a side length, we can double it to find a full side length, and then we can multiply that by 9 to get the perimeter of the entire regular nonagon. But let's back up and just find the apothem, okay? So if this is my reference angle, and I have one side that I know, the hypotenuse, and a leg that I don't know, this one here, I can use trigonometry to find my missing side. So if this is my reference angle, this side over here would be the opposite. This is my hypotenuse, and then this is the adjacent. So I'm going to use these two sides, the adjacent and the hypotenuse, the one I'm trying to find, and then one that has an actual length I can use. That's what we do when we're finding unknown side length using trigonometry. So with adjacent and hypotenuse, I have three choices. I can choose sine, cosine, or tangent. Cosine is the one that would make the most sense because that's the one that creates, it's the name for the fraction when you put the adjacent on top of a fraction on the numerator and the hypotenuse in the denominator. So that's the equation that I'm going to use. The cosine of some angle equals adjacent over hypotenuse. So the cosine of 20 degrees equals my apothem side over my hypotenuse length of 5. So if I take my calculator and I find the cosine of 20 degrees, I get about 0.9396926. And then if I just multiply both sides by 5, or you can cross multiply doing it this way, 1 times a is a, 5 times this value would give you an apothem of approximately 4.698 units long. They don't give me a specific, but just units. Okay, so I need this for my formula, right? That's one of my objectives. I need to find the apothem length, which was that. And now I need to figure out how to find the perimeter. As I said before, this side right here on this right triangle is exactly half of the side length of my nonagon. So if I could figure out how much this is, then I could double it to find the entire side length all the way across, and then take that and multiply by 9 to get the perimeter of the entire figure. So now I'm going to mark this with an X, and I'm going to ignore the adjacent. And now I'm really going to think about what trig function, sine, cosine, or tangent, I could use if I want to combine the opposite with the hypotenuse sides to find this length. Opposite and hypotenuse are part of the sine equation. Sine of an angle equals opposite over hypotenuse. So that would mean that the sine of 20 degrees is x over 5. So doing the same thing, I'm going to find the sine of 20 degrees on my calculator, which is about 0.342. I'm going to cross multiply. So x, which is half of a side, if I multiply this way, is about 1.71 units long. So if half of a side, that's about from here to here, the midpoint to point K, if half of a side is this long, Then a full side can be calculated by just multiplying that by 2, right? So one full side on my nonagon is about 3.42 units long. So if a full side is 3.42 units long and there are 9 sides, and since it's a regular polygon, all 9 sides are the same amount in length, then the perimeter, P, is going to be the number of sides, which is 9, times the length of each side, 3.42. So I get a perimeter of approximately 30.78 units long. So, remember, to find the area of a shape, I need the apothem length and the perimeter length. And again, the shape has to be a regular polygon. So here we go. Area equals 1/2 times the apothem times the perimeter for any regular polygon. So that'll be 1/2 times 4.698 times 30.78, which gives me approximately 72.3 square units. Remember to put the square on the words, not the numbers, so here, not here. And there you go. Okay, this is an equilateral triangle. Equilateral and regular are pretty much the same thing. It just means that all the sides are equal in length to each other. So this side is the same length as that side, which is the same length as that side. Okay, so obviously we have some central angles going on here. We've got a radius here, a radius here, and a radius here. So we have 3 central angles, right? 1, 2, 3. So each central angle is 360 divided by 3, or 120 degrees, right? 120, 120, 120. Now, they didn't give us a whole lot to work with to find the perimeter and the area of this triangle. I can find some angle measures. For example, this is 120, and if this is a true apothem, then this side would be 60. So basically, if I kind of grab this triangle right here, which is half of the bottom triangle, and draw it down here, this would be G and J and F in the center. Then this angle right here would be half of my central angle. So since the central angle is 120, then this corner would be 60. The other thing I know about this triangle is that the hypotenuse is 6. And so if I want to find the apothem is the distance from the center of the figure to the middle of a side. So that would be here. If this is my reference angle, 60, then this side would be my opposite. This is my hypotenuse, and that makes the apothem the adjacent side. So which of my 3 trig functions can I use to calculate the length of the apothem? Well, which ones incorporate the adjacent and the hypotenuse together? Well, the only one is, if our 3 choices are sine, cosine, and tangent, our choice would be cosine. The cosine of any angle is the name for the fraction when you put the adjacent on the top and the hypotenuse on the bottom of a fraction. So this would be the cosine of 60 degrees equals A for apothem over 6. So if I type in the cosine of 60 degrees on my calculator, I get 0.5. Writing that as a fraction, I can do that by placing a 1 underneath it. And then cross multiplying, I get an apothem length of 1 times A is A, 0.5 times 6 is 3. Now, the apothem is going to help us to figure out the area of this shape, but it's not really going to help us figure out the perimeter. So it seems our next step is to find the perimeter because it'll give us the first answer, and it'll help us, if we combine that number with the apothem, to calculate the area. So back up to this little right triangle that I've grabbed out of the shape. If I try to find the length of this side right here, that is exactly half of the length of a full side on this triangle. So if I can find the half length, I can double it to find the full length, and then 3 of these will give me the perimeter. So this, according to my reference angle here, would be the opposite side. And if I combine that with the hypotenuse of 6 and this reference angle of 60, using trigonometry, I should be able to find this length here. So which of my 3 choices, sine, cosine, or tangent, gives me the opposite side length of, uses the opposite side and the hypotenuse side? Well, that would be sine. The sine of an angle equals the opposite in the numerator and the hypotenuse in the denominator. There we go. So the sine of 60 degrees equals x over 6. So let's see, calculating the sine of 60 degrees on my calculator, I get 0.866 approximately. And then if I want to cross multiply, I need a proportion, so fraction on each side. I can create a fraction on the left by placing this over 1. Then if I cross multiply, x, 1 times x, is about 5.19615 units long. Now remember, that's just this length right here from J to G. That's just half of a side. So if I want to calculate the full side all the way across from H to G, I would have to double this length. So a full side on my triangle has a length of about 10.3923. Oops, not on the screen. There we go. Okay, so we finally now have, we're almost there to figure out the perimeter. Since this is a triangle, and one side has a length of 10.3923, to find the entire perimeter, I just take the number of sides, which is 3, times the length of each side, which is 10.3923. Multiplying those together, I have a perimeter of about 31.2 units. This is my first answer, the perimeter. Now the second thing they've asked us to find, we've been directed to find, is the area. The area is 1/2 times the apothem times the perimeter. So that would be 1/2 times apothem, which is 3, times the perimeter, which is 31.2 about. So I get an area of approximately 46.8 square units. Now the next page, I suggest you pause the video and try numbers 14, 15, and 16 on your own. Because I'm about to show you all the answers. So pause the video now if you don't want to see all the answers. Okay, here are my solutions to 14, 15, and 16 on the last page. And pause the video now if you'd like to write them down or check them.